We hope that the previous presentation got you started with Tolcap and showed how to predict the process capability of a tolerance dimension from process maps and considerations of the material and geometry of the part and some sources of additional variation. This presentation will show you some useful different ways to apply Tolcap by turning that question round. As I said, the previous presentation showed how Tolcap provides you with a prediction of process capability for the dimension and tolerance you specified. Now, if the Tolcap algorithm can get from dimension and tolerance to process capability, then it should be, and it is possible, to rearrange the algorithm to calculate the tolerance required on a dimension to achieve a specified process capability. Let's establish why you might want to do that. Working from required capability to tolerance has three useful applications. Firstly, is the final process, and by the way we always look at the final process that determines the dimension of interest, is the final process good enough to achieve the required tolerance capably? Do you need to ream those holes, or will simply drilling be perfectly adequate? Our next video addresses tolerance stacks, or stack-ups if you will. And it turns out that a good strategy to maximize capability of the stack, or to minimize stack tolerance capably, is to specify the tolerances for the stack elements for equal process capability. And Tolcap shows you the tolerances to achieve that. Thirdly, when working in this mode, Tolcap will show an optimistic and a pessimistic tolerance to achieve a required process capability. And this is particularly helpful if you're one of our users who is not at all confident in choosing geometry or process factors. To show how to use Tolcap in this mode, we will work through the same example as in the previous presentation. A dimension of 100 mm on a part that is turned and bored. Then we specified a tolerance of plus or minus 0.035 mm, but this time we'll specify a process capability, CPK. So as before, log in and select the process category for the manufacturing process that defines the dimension of interest in your design. Here, machining and turning and boring. This time, first click on the CPK tab, then enter 100 as the dimension, and click on the CPK box to see a drop-down choice for target CPK. You may enter any value between 0.05 and 4 as the target CPK. The drop-downs provide prompts for popular values. You may well have noticed that Tolcap defaults to a target CPK of 1.33. Why? The Tolcap approach reflects good practice at the time the algorithm was constructed, as represented by the Ford Motor Company's Production Part Approval Process, or PPAP, which required the supplier to demonstrate CPK equals 1.67 off the first off-tool run of the new part, and to ensure CPK be greater than 1.33 throughout production. The Tolcap prediction addresses that last clause, so our recommended default CPK target is 1.33. Just to link this to design for Six Sigma, if you can design to get a theoretical CPK equals 2, i.e. a band of plus or minus 6 sigma around the target dimension, then you have a margin of plus or minus sigma for that first production run. So, click 1.33, then calculate tolerance and ppm. And you will see the required tolerance to achieve CPK equals 1.33, or the equivalent 33 ppm reject rate, shows as plus or minus 0.017 millimeters. But that of course is for the ideal case, and as before we need to select the appropriate material, mild steel, apply the geometry wizard, apply the variation wizard and recalculate, and we will see that to achieve a CPK of 1.33, the required tolerance is plus or minus 0.046 millimeters. You can also see the result on a map. And let's recap the results we've got from this example. And you have the figures that when we selected a required tolerance of plus or minus 0.035, Tolcap predicted we could expect a CPK of 0.97. But if we ask Tolcap what tolerance we need to achieve CPK equals 1.33, it predicts that a minimum tolerance of plus or minus 0.046 millimeters should be specified. While our introduction describes the recommended way to use Tolcap, some users find it quite daunting. Okay, you know the dimension and tolerance. You can choose a process and material, but the geometry and additional variation questions don't necessarily have right or wrong answers. You have to apply some thought and judgment. Let's work the example once more, this time just supplying the process dimension, target CPK and the material. So select Machining, Turning and Boring, the CPK tab, enter the dimension of 100 millimeters, CPK 1.33, select the material as mild steel, click Calculate, and Tolcap suggests that under favourable conditions, minimal geometry effects and no additional variation, plus or minus 0.022 millimeters might be achievable. Well, we're well aware there might be part geometry effects or additional variation problems, but we don't know quite what those issues are at this point. But Tolcap can show us a range of tolerances, from that required for the most favourable conditions that we just obtained to, well, not the worst case, but the least favourable case that we can imagine in practice. So if you click on the Range tab, Tolcap shows that while plus or minus 0.022 millimeters tolerance may be process capable under the best conditions, at the other end of the scale the tolerance may need to be as much as plus or minus 0.063 millimeters. Well, that puts our original starting tolerance of plus or minus 0.035 into some sort of perspective and context. Of course, the more you put in, the more you get out of Tolcap. If we actually apply the geometry and variation wizards as before, the range chart will show the minimum tolerance predicted to achieve process capability for the entered conditions now, for the most favourable conditions, and for the least favourable conditions. We hope these introductory presentations have shown you why Tolcap is a unique and vital tool for designers. Setting achievable tolerances saves your organisation significant costs and saves you a lot of that stress and distraction sorting out designs that could otherwise turn out not capable. Tolcap helps you check the capability of a tolerance or generate a tolerance with a target capability. Our next presentation explores the problems of tolerance stacks or stack-ups and how Tolcap provides solutions. For more information, help and resources to get the most out of Tolcap, or to purchase a Tolcap license, please visit our website at www.tolcap.com.